Hi everyone. So this is the third and final video on properties of Bessel functions and their relationships with the Bessel equation. And we're going to show some computational ideas here that will come up in the exercises and ways that I expect you to be able to manipulate the Bessel functions. So the first thing is that in physical systems, it's typical that what we want is functions that have bounded behavior at 0. And from the properties of Bessel functions, it's pretty easy to see that Bessel functions of the first kind, that is, your sort of J alpha functions, J alpha of x, is bounded at x is equal to 0. And Y alpha of x, that is the Bessel function of the second kind, is unbounded. If you look at the graphs, you can actually see that the Bessel functions of the second kind dive off to minus infinity. Bessel functions are useful, or they came up originally in computations, because you could actually work with them using formulas that could translate Bessel functions of a certain order into Bessel functions of a different order. Which is to say, there are very easy formulas for integrating and differentiating Bessel functions of the first kind. So we're going to focus on Bessel functions of the first kind. And remember that those are defined by J alpha x is equal to the sum from k equals 0 to infinity of minus 1 to the k over k factorial gamma of alpha plus k plus 1 x over 2 to the k to the 2k. So that's a series that defines it. It's a series of even terms. And from the formula, it's pretty easy to show that certain properties hold. So the two big properties here are related to the differentiation of a Bessel function. So let's assume that alpha in this case is a... So here's the first property that turns out to be useful. X to the alpha times J alpha of x, if you took its derivative with respect to x, that's going to turn out to be equal to the same x to the alpha, but the derivative pushes the order of the Bessel function down by 1. Which is a pretty strange structural property, but one that turns out to be useful computationally. Property 2 says, so this is property 1, property 2 says that if you look at negative powers, that you get the same kind of relationship. So taking the derivative of x to a positive power times the J alpha keeps the x but reduces the order of the Bessel function. And if I multiply J alpha by a negative power of x, then I take the derivative. I still retain the x to the negative power out front, but I increase the order of the Bessel function. So these are things that can be proved. I'll leave that to an exercise, is to show this. If you're interested in walking through somebody else's proof, it's written out in the book. It basically just comes from differentiating the formula here and then rewriting it in terms of the Bessel function of the lower order. I guess the one nice thing about doing this is that you don't have to use the product rule, because you can put the x to the alpha inside and it will end up in the power of the x over 2. So if you have that x to alpha outside, you can push it in, take the derivative, and then pull it back out again. And what you're going to get out the other side is exactly what we have written here. So algebraically now we've got a way where we can write this expression so that we can reduce high order Bessel functions into lower order Bessel functions. And so these are the next two computational properties here. So property 3, that a Bessel function J alpha plus 1 of x can be rewritten as a combination of a Bessel function of order alpha times 2 alpha over x minus a Bessel function of order alpha minus 1. So ultimately, the point of this property is that all Bessel functions, presuming that alpha is an integer, can be expressed in terms of J0 and J1. So all higher order integer Bessel functions can be rewritten to be in terms of J0 and J1. And that's a pretty strong structural property. The fourth computational property that we're going to want is that the derivative of a Bessel function of a given order is a combination of the Bessel function of the previous order and the Bessel function of the next higher order. So again, in particular, this is going to let us say more when alpha is equal to an integer. So again, this is going to allow us to say more when alpha is an integer. All right, so how can we use these kind of expansion properties? Well, one thing you might do is you could say something like, find an expression for J2 of x in terms of J0 and J1. Then do it for J of 3. So these are pretty strong properties, right? When you really only need to know two functions in order to construct the rest of this huge family. So we're just going to use our computational formulas to do that. So the expansion of J2 of x, if I use the formula, it's going to be, so if this thing right here is alpha plus 1, then I write 2 over x times alpha, which in this case is 1, times the reduction of an order, which gets us down to J1 of x, minus J0 of x. So if we go up here to the formula, we can see the relationship is, this is an alpha plus 1, that's the 2 for this problem. These are alphas, which are 1, and this is an alpha minus 1, which is 0. Pretty straightforward application. So this is just 2 over x, J1 minus J0. If you want to go one step further, J3 of x is equal to 2 over x times 2 J2 minus J1, but J2 is equal to this, or better yet, this. And so what we end up was that J3 of x is equal to 4 over x times 2 over x J1 minus J0 minus J1. So I've just replaced J2 with what it's equal to, and that gets us 8 over x squared J1 minus 4 over x J0 minus J1, which you can rearrange into 8 over x squared minus 1 J1 minus 4 over x J0. So as the Bessel functions get higher in order, the combinations of the J0 and the J1 get more complicated, but it's nice to know that in theory, we can actually write down express formulas for Jn of x, where n is some integer, in terms of our starting Bessel functions J0 and J1. Another kind of exercise I'm interested in looking at is the gamma function. So remember that the gamma function of x is supposed to be equal to the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. Okay, this was the function that produced the factorials. In particular, gamma of n plus 1 is equal to n factorial. That's what the gamma function does, is extends the factorials to non-integer numbers. So from here, we can play all kinds of games because the form of this function is very special. What we might like to do is to see if we can figure out an expression when we have an integral that looks like this. So the question says to express the integral 0 to infinity of t to the p minus 1 e to the minus at dt in terms of the gamma function. Now this integral is not a gamma function because of this a. So what's our strategy going to be? Well, if I have an integral that looks like this and I want to make it look like that, then what I should do is I should use a substitution, a change of variables, to fix the problem so it has the right form. So what would that look like? Well, why don't we let u be equal to at, so that du is equal to a dt. And then everywhere I see a t, I'm going to have to write a u over a. Pretty standard substitution. And it's going to be the case that u of 0 is just a times 0, which is 0. And u of infinity, which really I should not think about, but what u of infinity really means is the limit as b goes to infinity of u of b, which is just a times b. Well, that's still infinity, right? It runs away to infinity. So after the change of variables, this problem becomes the integral from u equals 0 to u equals infinity of, well, here's a t, so that gets replaced with u over a to the p minus 1, e to the minus u, and then dt has to be replaced with an a dt, a 1 over a du. Well, it's still not a gamma function, but it's closer now. So what I can do is pull all the constants out. And what's that going to get me? Well, I've got a 1 over a that came from right here. And then I've got this a to the p minus 1 living in the denominator of this variable. So I can pull that out as well as a 1 over a to the p minus 1 times the integral from 0 to infinity of u to the p minus 1 e to the minus u du. And now this guy is a gamma function. In fact, that's equal to gamma of p. So outside we have a 1 over a to the p, and all of this is gamma of p. Because remember, the variable is a dummy variable. You're going to be evaluating it. It doesn't matter if it's u or t or n or x or whatever. That is gamma of p. And so this is the answer. 1 over a to the p gamma of p is what you get when you start with the integral t to the p minus 1 e to the minus at dt. So the ability to manipulate the gamma function integral is going to be another thing that I would expect you to be able to do. And there'll be some exercises to that effect. Some pretty interesting ones too. In fact, one of the things that we're going to show, it's kind of striking actually, is that gamma of 1/2 turns out to be equal to the square root of pi. Why ever that should be true is a serious question. How could that possibly be true if gamma is the function that reproduces the factorials? How is pi showing up in here? So I'm very interested to see you guys work your way through that problem as well. All right, so these kind of computations and manipulations of the Bessel functions and the gamma function are what I'm interested in you guys being able to do. And what I want you to carry away from this portion of the class is that, one, we get the sort of theory type stuff where we can manipulate these things, these really powerful formulas. And on the other hand, they drive this incredibly rich approximation theory. All right, so get to it. See ya.